Okay. Hello, everyone. Welcome to another episode of History of Science and Technology Q&A. So I see we already have a whole bunch of questions here. Some may have been saved over from last week. Let me see. What should we try and tackle first? There's a question here from Mikhail. What is the history of the discovery of black holes? All right, let's talk about that. So actually, the story of black holes, I think, goes back a long way. See, what is a black hole? A black hole is something where effectively light can't escape from it because there's too much gravity. And so, for example, when we look at the Earth, we say, how fast do you have to go to escape from the Earth? What is the escape velocity of the Earth? The answer is 25,000 miles an hour. What's the escape velocity of the sun? I think it's about 100,000 miles an hour. What's the escape velocity of the galaxy? I think it's about 1,000,000 miles an hour. It's things of different masses and different sizes have different escape velocities. And I think Laplace, back even maybe in the 1700s perhaps, had identified the fact that you could imagine a star that had so much mass in such a compact area that its escape velocity would be more than the velocity of light. And so, than the speed of light. And so then that would mean that you could have this thing and even light couldn't escape from it. So that was kind of an idea that existed there. Okay, so that was the kind of the prehistory to the study of black holes. Then in the kind of the theory of gravity, well, that was based on Newton's theory of gravity. So one of the big things that Newton did in 1687 when he published his Principia Mathematica was to make a proposal for a mathematical theory of how gravity works. I mean, people had had the general notion that things fall under gravity. Galileo had various points to make about the mass, the inertial mass versus gravitational mass. You know, Aristotle had a very simple thing to say about gravity, which is that sort of things tend to want to be closer to the center of the Earth, and that's why they fall. But Newton had a mathematical theory of gravity, and his universal law of gravitation was the idea that there is an inverse square law, that the force of attraction between objects due to gravity is 1 over the distance between them squared. And you know, I find it somewhat interesting that that universal law sometimes even got applied in fields completely different from physics. I know in geography for a while, there was sort of a law of retail gravitation, which said, you know, people who are coming to different shopping centers, you know, how far away, how much will they be pulled towards one shopping center or another? And obviously that's not actually a force of gravity, but it's sort of interesting that these other areas adopted, I think perhaps a little bit by mistake, this kind of universal word, the universal law of gravitation. For Newton, what the universal meant was it applies to the sun versus the Earth versus things falling on the Earth versus a comet orbiting, you know, in the solar system, universal in that sense, universal between all bodies with mass, whether they are terrestrial or whether they are whether they're in the sort of broader universe, so to speak. So anyway, Newton's theory of gravity had been the one that had been used from 1687 until the beginning of the 1900s. And by the way, you know, it's an interesting story. I think I've perhaps told it before that, you know, when you ask the question, is the theory right? Newton certainly figured out things about the orbits of comets and things based on that theory, but the big prize, and the big prize for mathematical physics through the 1800s, was the theory of the moon, the theory of the motion of the moon and the gravitational attraction of the Earth and the sun and other planets on the moon, and could that correctly account for the motion of the moon and things like when eclipses would occur. Very hard problem. We now kind of suspect it's sort of a computationally irreducible problem, but then it was just a hard problem with a lot of math that had to be figured out to make it work. And Newton, when he first tried to do this in 1687, got the wrong answer, and he knew he got the wrong answer. He didn't know why he got the wrong answer. As it turned out later, it was a question of what approximations you use, et cetera, et cetera, et cetera. And it took, you know, a couple of centuries to really work through and get to the right result. But anyway, so theory of gravity based on Newton's inverse square law. Laplace had noticed that you could have these sort of things where light couldn't escape. Then we go into the beginning of the 1900s. And the question then was, did anybody need a new theory of gravity in the beginning of the 1900s? Not really. Newtonian gravity was working absolutely A-OK. But then Einstein, in his special theory of relativity in 1905, kind of realized that one should think about space and time differently than they had been thought about before, in particular in trying to sort of reconcile Maxwell's equations for electromagnetism with mechanics. He realized that you really had to change the definitions of space and time. And we kind of think we understand in recent times with our physics project a little bit more about how that works. But nevertheless, Einstein had this idea that you had to be able to not just have a fixed notion of distances in space, but they had to be things where, depending on what reference frame you're using, which could be a question of how fast you're going, things like that, you get different answers. Okay, but then Einstein was curious, sort of how did gravity relate to all of this? And in special relativity, he had this idea that different reference frames, if you're traveling at different speeds, you kind of can't tell the difference between, if you're in sort of a closed box and you're just doing your experiments and so on, you can't tell how absolutely fast you're going. It's always the same inside that closed box, not relative to anything else. Physics always looks the same, regardless of what reference frame, for example, how fast you're going. Okay, so then he wondered about gravity. And so what he came up with was kind of an analog of his principle of relativity, which pretty much said you can't tell how fast you're going, wanted something analogous to that. And so he came up with this principle of equivalence, which said you can't tell whether you're accelerating or whether you're in a gravitational field. That a gravitational field is kind of something that is something related to the description of space and time that's just to do with your state of acceleration rather than needing to be talked about as a thing in itself. And so that led to the theory of general covariance, and it led, after some flapping around, in 1915, Einstein came up with his general theory of relativity, which is a description of space and space-time. And the main point of it is to say that space can be curved in response to the presence of energy momentum or the presence of mass in space. So, in a first approximation, sort of when you have let's say a light beam, a photon traveling, a laser, something like this, it'll go in a straight line. But the question is, what does straight mean? And the question is, can space be curved in such a way that the, quote, straight line, the shortest path between 2 points, the geodesic between 2 points, is something which, at least looked at from the outside, would look curved. And we certainly know that if we were to have, I don't know, some rubber sheet, and we were to sort of press down on the rubber sheet, we would have the paths that things would take to be shortest paths on the rubber sheet would deflect around the place where we sort of press down on the rubber sheet. Okay, so then what Einstein suggested in the Einstein equations is that the curvature is proportional to the amount of energy momentum in space. And so that's the basic form of Einstein's equations in general theory of relativity. And it says space gets more curved when there's more mass in it. And the curvature of space then leads to the deflection of anything that goes through space. And so that is how gravity is derived. And it actually works the same way in our recent fundamental theory of physics, although the way that the structure of space works is different. But the basic idea that there's sort of a curvature in space that leads to deflection of sort of test particles, or leads to something which seems like a force of gravity that deflects things. You can interpret it as a force of gravity deflecting things, or you can interpret it as a curvature, a deformation in space-time. Okay, so that was in 1915. Einstein came up with this general theory of relativity. Nobody really knew if it was correct at that time. It was certainly mathematically elegant. David Hilbert, kind of really week by week, as Einstein was deriving the general theory of relativity, they were kind of both working on very related things. So that's why it gets called the Einstein-Hilbert action. That's the form of the thing that you minimize or extremize in working out how relativity works and curvature of space-time. Okay, so then very soon after Einstein published his equations, people started trying to figure out, okay, so what are the solutions to these equations like? Famously, one feature of those equations is that their most immediate form says the universe should expand. And Einstein was like, but the universe is obviously not expanding. So he had to put in an extra term, the so-called cosmological term or cosmological constant, that kept the universe from expanding. It's kind of a hack to keep the universe from expanding. Now, maybe 15 years later, Edwin Hubble observed that there was actually a Doppler shift of the light coming from distant galaxies. So he showed the universe actually was expanding. And that was sort of it's a lesson to those of us who try and make theories of things that the elegant theory might actually be right. And you should ask whether the experiment has even been done before you start hacking your theory to make it agree with what you think must be true based on experiments that maybe haven't even been done. So in any case, that was, so that was one sort of prediction of the Einstein equations. Now, I think by 1916, Karl Schwarzschild had found a solution to the Einstein equations, a spherically symmetric solution, asking the question, if you kind of have a bunch of mass somewhere, what will be the gravitational field associated with that mass? It's the same kind of question you could ask for Newtonian gravity, and actually, in many respects, you get the same answer. Okay, so Schwarzschild had this solution. Unfortunately, Schwarzschild was killed in World War I. But he had this solution, and everybody said, okay, fine, it's a solution to the equations. If you have a massive object, this determines, for the spherically symmetric case, what the gravitational field will be. All good. Okay, there was a weird thing, though, about the solution, which was that in the actual mathematical formula for the solution, there was a singularity. That is, there's a term that where the actual metric tensor, the actual thing that specifies distances based on coordinates and so on, goes to infinity. And everybody said, well, we don't really know what this is, but don't worry about it. It's probably just some mathematical glitch. And that's the way things were until pretty much the 1940s. And at that time, people started studying the actual collapse of stars. People had better understanding by that time of stars operating by nuclear fusion, things like this. Famously, Robert Oppenheimer and a person called Snyder worked on the Oppenheimer-Snyder model of the sort of the collapse of stars, thought to be relevant for things like supernovas and so on. And when they did that, they kind of pulled back out all these questions about okay, so what really happens in Einsteinian gravity in that case? The thing that but it wasn't really known that the Schwarzschild solution was there. It had this weird singularity. Nobody really knew what that was. By the way, that singularity was somehow sort of related to the idea that the old Laplace idea that there could be sort of a more than speed of light kind of escape velocity, those kinds of things. But there was kind of what would actually happen when a star collapses and when there is a total amount of mass that ends up being larger than where this amount of mass is collected within the so-called Schwarzschild radius of the black hole, of the gravitating object. I shouldn't say black hole yet. So okay, so that's where things stood at that time, and people started trying to make measurements of, was Einstein's theory of gravity correct? There had been one particular measurement that had been made in 1919 of the bending of light around the sun, made by Arthur Eddington and friends, in which the Einstein gravity had predicted that light would be bent a factor of 2 more than Newtonian gravity said it would be bent. And that was a validated result. But so far as I remember, there were no other direct tests of Einstein gravity for many, many years after that. But anyway, so people were then starting to think about collapsing stars, but there was still sort of, then it was confusing about this coordinate singularity. Then people realized it was just a singularity in the mathematics. It wasn't nothing really happened there. Well, kind of nothing really happened, but actually something did happen, because that was the place where sort of light couldn't escape from it. It was a thing which later got called an event horizon, a place where things can have an effect from the outside, can have an effect in, but from the inside can't have an effect going out. But people were very confused about what that singularity versus event horizon and so on might be. It took until the 1960s, I think, before, let's see, there's these things called Kruskal coordinates. I certainly knew Martin Kruskal a bit. I think those were developed in maybe the 1950s or even the early 1960s, was a way of setting up coordinates so that you didn't have this sort of this immediate singularity, and you could kind of a little bit more effectively analyze what was happening in this situation. And it really took until a lot of analysis by people like Roger Penrose and so on of just what really happens. What are the ways that things from the outside can have an effect in, from the inside can have an effect out, to establish this idea that there would be event horizons, that there would be this thing that in the black hole, there would be an event horizon. And the term black hole, I think John Wheeler suggested that term as kind of a little bit of a you can't be serious, this isn't a real thing kind of term. And nobody knew whether an actual collapsing star would form a black hole, or whether matter, in the sense that it would form an event horizon and would have this feature that nothing could escape from it and so on, or whether matter, as matter actually is, would always bounce. The star was collapsing, but maybe when the force of gravity was so strong, things would always bounce. That would just be a feature of the so-called equation of state for matter. Nobody knew. And that wasn't even up until the 1980s. That was not known. It wasn't really known. People imagined that there was a critical mass, and you could above which you would form a black hole, but nobody really knew. Nobody knew the dynamics of how that would work. And people wondered, would it be a spherical collapse? Would the things spurt out in different directions? All these kinds of things. And so it was all a bit mysterious. And it didn't, it didn't help that the whole idea of the Schwarzschild solution to the Einstein equations, it's very confusing, because the Schwarzschild solution is a vacuum solution to the Einstein equations. Even though you're told, oh, it's a solution for some spherically symmetric thing that's like a star, there's no star inside. There's nothing inside the Schwarzschild solution. There's this event horizon, but inside, everything is just hunky-dory until you get to the very center of this spherically symmetric thing, at which point there is a singularity in the curvature. And so, in a sense, in the way that the standard general relativity is set up, that's a place where you're essentially punching a hole out of the universe. And you're saying, our equations don't apply just in this tiny little hole in the center. So that was a very confusing thing. And, whether you can, now it could be the case that there are sort of fragments of crushed star inside this thing, which on the outside is governed by the Schwarzschild solution. But it turns out it doesn't matter whether there's crushed star inside there, whether there's just this hole punched out of the universe at the center. You still get the same results for what the gravitational field looks like outside. So that was all very confusing. And I certainly was not sure that black holes existed. In the 1980s, it was really unclear whether that would actually be a real thing. And so, for example, there was a star, Cygnus X1. It was an X-ray emitting star. And the theory was that Cygnus X1 was a binary star system where there was maybe just a single star actually in that case, where if there is a black hole, then matter kind of spirals into the black hole. And as it spirals in, as it gets closer and closer to the event horizon and so on, it has more and more, and it's going faster and faster, and that causes it to emit more and more radiation, even to the point where it's emitting X-rays. And so that was sort of a theory for what Cygnus X1 was a matter and accretion disk around a black hole spiraling into the black hole. But it didn't really matter that it was a black hole. It could have been some neutron star or something like this, some other thing which wasn't really a true black hole in the Einstein relativity sense. Now, meanwhile, during that period of time, there had been all kinds of, let's modify Einstein gravity for this reason and that reason. And there was the so-called parametrized post-Newtonian framework, which was a way of sort of describing perturbations to Einstein gravity that could exist. And people were looking for, when spacecraft went out in the solar system, would there be deviations from what you would expect there? There were some nice experiments, precision experiments done with satellites, looking for various kinds of effects that were predicted by general relativity. And general relativity kept on getting check marks. It kept on working. There kept on being other theories that were like, oh, a bit more complicated than general relativity or different. General relativity kept on working. When people started thinking about the quantum theory of gravity, people, and that was particularly true, I would say, in the late 1950s, early 1960s, there had been a lot of success with quantum electrodynamics, which was involved kind of looking at photons and virtual photons as the sort of carriers of the electromagnetic force. So the obvious question was, could there be gravitons, which are carriers of the gravitational force? And a bunch of people, including my friend Dick Feynman, looked a bunch at, could you just make a theory that was like quantum electrodynamics, but for gravitons? And different people had different theories about this. And there were all kinds of sort of technical issues that came up in that theory, particularly to do with the phenomenon of renormalizability, which have been found to very nicely deal with the infinities in quantum electrodynamics. The same approach didn't work for gravitational theories. And there were funky things, like, for example, John Wheeler, Dick Feynman's thesis advisor, among other things, and the inventor of the term black hole, I think, wrote this whole book about what he called geometrodynamics. And in some ways, it was a precursor to some things that I've worked on to do with the discreteness of space-time and things like this, and had some very nice analogies. And I was always curious why this book was so obscure, because it seemed like it must have introduced some quite interesting ideas. And I finally recently, with some difficulty, got myself a copy of this book. And here's the reason it's so obscure. It had the theory that gravitons were neutrinos, which is completely wrong. So neutrinos are these particles that were discovered, were suggested by Pauli in the 1940s, I guess, as a feature of nuclear beta decay, and then were first actually detected in the late 50s or early 60s. The idea that and they're very weakly interacting particles that will like go all the way through the Earth without interacting. And this book by John Wheeler is a book that has a lot of interesting things in it, but it has this completely wrong idea that gravitons might be neutrinos. So it's kind of a lesson in factoring one's kind of ideas, in the sense that the other ideas there about discrete spacetime are perfectly valid ideas, but the idea about gravitons and neutrinos is not a valid idea. But in any case, so it was all a rather confusing thing. But then the notion of kind of the mathematics of black holes got better and better developed. And people started studying the mathematical structure of the solutions to Einstein's equations and so on, and started establishing that the Schwarzschild solution and the Kerr solution, which is for rotating black holes, were in some sense sort of the all you needed, and there weren't other details about, oh, you might have a star that has a weird little elongated shape, and does that have an effect on the black hole that forms? And the answer is probably no, and so on and so on and so on. Now, there's another thing that happened in boy, you guys are really pushing me on dates here. I think 1973, if I remember right, was Stephen Hawking came up with this idea of Hawking radiation, which when I first heard about it, I was like, who knows whether this is correct or not? Because the theory of gravity and black holes and so on is a classical theory, is a classical physics theory. It has nothing to do with quantum mechanics. And the description of what happens in the event horizon around a black hole, it's all classical physics. What Stephen Hawking did was to say, well, what happens if you have a quantum field which has its quantum field fluctuations, and it's happening right close to the event horizon of a black hole? But the event horizon is still described classically. And sort of the qualitative picture is, you will have these particle-antiparticle pairs that are spontaneously being created in the vacuum, and maybe one of the members of that pair will be pulled into the black hole, into the event horizon, leaving a kind of a lone other member of the pair, which can no longer annihilate with the thing that got pulled into the black hole. And so that lone member will escape to infinity, and that will be radiation from a black hole. And so I had no idea if that was really right, or whether when you did a more accurate rendition of the event horizon of a black hole, including quantum effects, whether there be these little fluctuations in the event horizon, which would always keep on, whenever there was a pair formed, it would keep on, the event horizon would kind of fluctuate to the point where that member of that pair would always be either on one side or the other. It was completely unobvious whether that calculation that Stephen Hawking made was in fact a physically correct calculation, or whether it was just something you got by putting, one approximation on top of another approximation. To give you an example of something back in maybe 1981 or so, I did this calculation of the effect of vacuum fluctuations, not in the case of a background gravitational field, but if you just put the vacuum fluctuations in a box. So let's say a metal box, you put the fluctuations in that box and you say, what effect does that have on the box? And it turns out the presence of vacuum fluctuations between like parallel plates produces a small force of attraction between the plates, essentially because there are more fluctuations outside the plates than inside. You do that inside a box, you get all kinds of weird effects. It later became clear that the stuff I'd worked out had the consequence that you could actually extract energy from the vacuum by just changing the shapes of these boxes and so on. But it was an approximation based on taking a classical box and a quantum field inside. And I never believed that result because I always thought that anything funky that happened there would be a consequence of the approximation you'd made with the classical box. And it turns out probably that's the case, that the box sort of can't be opaque to sufficiently high energy radiation. And so that's why it doesn't go to approximation. But what people imagined with Hawking radiation, or what Stephen Hawking imagined, was in the case of event horizons, for some reason, there wouldn't be any of this sort of mismatch of approximations and the effect would be real. Now, nobody observed that effect. At the beginning, people noticed that if there was about a 10 to the 15 kilogram, I think, black hole formed at the beginning of the universe, I think that's a mass about the size of Mount Everest or something, such black holes would be exploding. So the way Hawking radiation works, it sort of is very, very gradual for a long time. And as the black hole gets smaller and smaller, it gets more and more intense until eventually there's sort of this burst of radiation at the end of the black hole, so to speak. And people imagine that maybe that would be observed of primordial black holes from the beginning of the universe, but it wasn't. And so Hawking radiation, to sort of spoiler, Hawking radiation has never been observed. So we don't know whether Hawking radiation really happens, although at this point, the theory is sufficiently well developed that it probably does. And by the way, somewhat confusingly, there is a similar kind of radiation from acceleration that maybe has been observed in particle experiments, although it's sort of controversial what the interpretation is. But in any case, so back to black holes. So it was then, people said, oh, well, there must be lots of black holes, and there were more things identified, things like Cygnus X1 identified. There was this idea, oh, there are probably black holes in the center of our galaxy. There might be big black holes in the center of a galaxy, but it was all a bit unclear. And it was a bit unclear whether a thing with just a lot of mass is different from a formal black hole in Einstein's theory with all of these event horizons and all these other features. And I have to say, it wasn't for me until gravitational waves were detected about 5 years ago that I finally got convinced that black holes are actually real. And the way I got convinced is that the way that computation works, it really depends on the fact that there are two black holes and they merge into one spherical black hole. And it's not obvious that would happen. And it's not something that, if it wasn't something for which the formal sort of notion of event horizons and so on really worked, it's not clear that that would go that way. And so to observe that and to observe the little ring down as you make this kind of bell-like thing that is kind of like you hit the thing, you hit the black hole, and it wobbles around a little bit like a bell and it emits gravitational waves. I mean, it sounds very peaceful, but actually it in a few seconds, 1.5 times the mass of our sun was converted into energy. And the result of that in gravitational radiation was detectable by us 1/3 of the way across the universe. So it wasn't a particularly peaceful event. But in any case, by the way, just in the last month or so, we've got results from our model of physics that give the exact same kind of ring down for a black hole computed using our model of physics. So that's interesting as well. But in any case, so the discovery of black holes was a bit of an interesting mess, because the sort of mathematical belief that something like that might exist was it an artifact of the mathematics? Was it real? This took a long time to resolve. And I would say that it's only quite recently that it's really clear that that's right. And for example, the full scope of where black holes are important is still not known. I mean, I remember back in probably 1975, I remember going to some talk. I was young then, but going to some talk given by some fairly well-known physicist, and I asked the question afterwards. It was a talk about black holes, I guess, and I asked the question: could particles like electrons be black holes? Oh no, that's a very silly idea. Couldn't possibly be, irrelevant, etc., etc., etc. Turns out it might actually be true, but but that's a very different sort of interpretation of a black hole-like thing from what one imagined, which was it's all collapsing stars and things of that kind, or it's just features of the mathematics. And it just wasn't clear whether it was physical or whether it was just a feature of the mathematics. I mean, there are plenty of situations in which there are kind of features of mathematics that say something, but they're not real. They're just a consequence of, for example, the particular choice of coordinates you've made. And it's not something which, when you actually observe it physically, will be there. So anyway, long discussion about the history of black holes. And I think the sort of the quantum effects for black holes, not yet observed. In our models, there are some particular kinds of predictions about that might conceivably be observable. But so far, the best we know is that when black holes merge, they seem to do it in the way that general relativity says, very accurately so. It's always a sign for physical theories so there's one thing when there's kind of an easy prediction, and you say, okay, given my theory, I can immediately predict the following will be true, okay? Given my theory of the inverse square law of gravity, I can kind of immediately predict that the trajectories will be conic sections, like ellipses and things like this. Well, somewhat immediately. There's a little bit of math involved. But in a sense, the theory gets more points the deeper the math that's involved to get to the prediction. So, sometimes, because it kind of feels like it wasn't a put up job, in the following sense. If you have a theory where underneath the theory, there's something that says, oh, there's this particular thing, you work it out, and then you go through all this work, and then you say, okay, I predict the following, you go and measure it, and that's what you actually discover. That seems very convincing, because it seems like you didn't put that effect in from the beginning. It just was something that emerged from the structure of the theory. It's kind of, it reminds me of sort of clinical trials where, is it an effect where the patient knows they got the placebo or not? Well, you can't control this thing. You just start off with a little theory, and then you work out all this fancy stuff, and then you say at the end of it, do you get the right answer? So general relativity does really well from that point of view, because it's really hard to work things out. The actual computation of a black hole merger is a complicated thing. People end up using our Wolfram language technology stack to work out all kinds of things about sort of the symbolic description of the tensor expressions and so on. And then eventually it turns into a big numerical analysis adventure to work out the final details. But so this idea, there's a big tower to get from the theory to the prediction, gets you a lot more points. And in our theory, for example, now, those towers are going to be pretty big. And of course, somebody has to do the experiment and they have to come out right. But that will be very high leverage results, because there is so little going in, so much work to get to the prediction, and then in a sense, so much that comes out. But that's okay. So anyway, that's a little bit about the story of black holes. And I think one of the remaining mysteries about black holes is, I mentioned that at the center of a Schwarzschild black hole, there's this singularity in space-time, this point that's punched out of the universe, so to speak. Well, presumably, at least in the formal version of the mathematics of that. In a Kerr black hole, a rotating black hole, that was a solution to the Einstein equations that was discovered much later, maybe in the 1960s, that represents something that has angular momentum. In a Kerr black hole, there's an event horizon. It's a bit more complicated. There are two event horizons, but basically there's an event horizon that doesn't let effects from inside the black hole ever get out unless the black hole is spinning really fast. If the black hole, if the angular momentum J in some units is larger than the mass M, then there will be a naked singularity. You will be able, without an event horizon shielding it, you'll be able to actually sort of see in from the outside world to that singularity, to that place where there's something broken in the universe, so to speak. Well, turns out when you look at black holes that are observed, there seem to be a bunch that have more or less critical angular momentum, but none that seem to have supercritical angular momentum. That kind of suggests that somehow there's some mechanism that shields the naked singularities, that prevents naked singularities from forming. Now, you might think, in terms of the history story I told, well, okay, so there's a mechanism that prevents naked singularities forming. You know, back in the past, it's a very detailed thing that, well, you can form a black hole, but you can't form a rapidly spinning black hole. So it wasn't obvious you could form a black hole. It might have just bounced. And it's now believed that you can't form a rapidly spinning black hole. And in fact, this question about naked singularities, there is some very elaborate construction that allows you to get sort of something that's like a naked singularity. But one of the things that we suspect from our theories is that the presence of a naked singularity requires kind of a sufficiently complex description of space-time that it's not possible for a computationally bounded observer to have such a description, and that's sort of why you don't get this. But that's that's another wrinkle in the whole story of black holes, is they imply singularities in space-time. They imply basically what they're basically saying, and it's a very weird thing. The Einstein equations are supposed to be equations for space-time, and yet the Einstein equations are announcing to you, sorry, we don't work at this point. And that's a very weird thing. And it does happen with other kinds of equations, but it is something where, you know, it's like you have to be a little bit suspicious. You've got these equations that are supposed to describe space-time, and yet they put up a flag and say, we don't work in this place. And how do you interpret that? And that was a long story to get to the point where people feel comfortable with that interpretation, maybe too comfortable with that interpretation, and there's sort of more story to be had. So for example, in our models, we can actually study the formation of supercritical black holes that are spinning faster than their mass, so to speak. And what happens in our models is something very bizarre that you couldn't see in general relativity. What happens is, in our models, a piece of the universe simply breaks off. And in general relativity, the universe space-time is described by this manifold that doesn't have the possibility that it can change its topological structure, so to speak. It can't break off, it can't change its dimensions and so on. But in our models, we can explicitly see, in this case, that things break off. And so hopefully we'll be able to analyze a little bit what happens to various kinds of black hole mergers and so on, and when things can break off, a very weird phenomenon, and get sort of a more physicalized description of what's going on, when the Einstein equations just say, well, this is what we conclude, but we can't really give you a physical mechanism for what's happening. All right, long answer to that question. Interesting question, thank you. Okay, so many more questions here. Let's see. It's a question from Idiod. Is gravitoelectromagnetism sufficient to get black holes with event horizons, or do you need the full general relativity? I think you need full general relativity. I think a charged black hole, a Reisner-Nordstrom black hole, has yet more tentacles to it, but you basically just need the Einstein equations to get event horizons. Okay, there are questions here about okay, a few more questions on this sort of gravitational direction. Parmenides asks, did I ever meet Stephen Hawking or Chandrasekhar? Yes, I certainly did meet Stephen Hawking. I met him right at the time, you know, he had ALS, neurological disease, for many, many years, survived just a very, very long time. But I met him right at the time when he was still just about able to talk, but it was really hard to understand him. That was in the, when must that have been? That must have been 1980-ish. And I always I thought that one of his impressive personal achievements was just he just had this terrible neurological disease which made it difficult for him to communicate and to do sort of the ordinary things people end up doing. And he ended up persisting. I mean, he was a person with a strong personality, I would say, who ended up persisting in doing physics rather than just sort of giving up on the whole thing, which was certainly an impressive feature. I mean, I do remember when back in, it must have been 1980 or so, pointing out to him that there were all these kind of computational methods that you could use to be able to type, even though you couldn't, even with paralysis and so on. And I was always a bit surprised he wasn't that interested in that stuff at that time. I mean, he always had a group of kind of humans assisting him. Later on, I think he got much more involved in using technological solutions and so on. That was a good thing to see. Chandrasekhar, who is a person who studied a lot the kind of stability of collapsing matter and things like this, was a person at the University of Chicago. I never met him. Let's see. Parmenides also mentions Ernst Mach, who I don't know all that much about, I have to say. Mach was interesting in the history of mechanics for these ideas about things like, where does mass come from? Maybe mass is the result of the effect of gravity from all the other masses in the universe. In the end, I don't think that's really the right picture, but it's an interesting picture, and it's one that I think influenced Einstein. I mean, Mach also discussed the question of rotating, if you're spinning around, and how do you know you're spinning relative to, is spinning something that has sort of relativistic kind of consequences? And I guess, again, I've not really, have less understanding of that than I might. There are some weird solutions to Einstein's equations that involve spinning universes that have all kinds of strange effects, particularly closed time-like curves, that is, being able to essentially travel in time like you do in space, something which I don't think is possible given our current models of physics, which very much distinguish space from time. I mean, one of the things about the early history of relativity, in 1905, Einstein kind of came up with a special theory of relativity, which has certain mathematical features. And one of its mathematical features is that it is full of x squared minus c squared t squared. It's that particular form, distance minus speed of light squared times time squared. It shows up all over the place. And in 1909, a chap called Hermann Minkowski, who was a mathematician, primarily a number theorist, sort of got hold of that kind of structure and said, yes, we can make a geometry around this kind of relativistic notion of space and time. And he said, and that geometry looks just like what he'd studied in theory of quadratic forms in number theory. And so in that very nice, very mathematically elegant geometry, space and time become the same kind of thing, because they enter in sort of the same way in these formulae and so on. And so that led to this idea of space-time, and time is just a dimension like space, and it led to endless, time travel type stories, although H.G. Wells's time travel book, I think, Time Machine book, predated that discussion. It was in the late 1800s. But I think this kind of idea of Minkowski's, from a matter of mathematical elegance, kind of led to this whole space and time, the same kind of thing, which led to a whole development in physics that I think went off track. Because I think what has become clear from our models of physics is that time is associated with sort of the inexorable computation of future states of the universe, and space is associated with just extension of kind of the data structure that represents the universe. Now, actually, I just wrote a piece about consciousness, and so that's led me into a bunch of interactions with philosophers and so on. I was just exchanging mail with a philosopher I know, who actually, of all strange things, know from elementary school, but he's become a distinguished philosopher. He was pointing out that this notion that time is different from space, that actually Aristotle already had a notion of time being associated with transformations of things, which is pretty much the same idea as our idea of time being associated with a progressive computation in the universe. So it's kind of one of these cases of where, yeah, well, the obvious thing turns out to be right. I mean, a lot of what Aristotle said about physics, for example, turns out not to be really on the mark. But this is sort of an obvious observation about what time is, and it seems like that's pretty much what time is. And the sort of the mathematical elegance of what Minkowski did that led to Minkowski space and all these kinds of constructs in relativity seem to kind of have led people a bit astray. And it's kind of a lesson in history of science of sometimes it's, I was talking about, if you have an elegant theory, go with it. But sometimes the elegance can lead you astray, and you could be led to an analogy which isn't really a correct analogy. So let's see. All right, there was a question here. Oh boy, there's a question at the end here about, but I want to address a few others here. But there's another this question from Frost: is there an instance or phenomenon where an instrument uses a theory, and is there something like Gödel's theory that applies to instruments in physics? The answer to that is very much yes. It relates to this idea of computational irreducibility that I've studied a lot, that has to do with how do you know what's going to happen in a system in physics? Well, one thing you can do is just sort of look at the underlying rules of the system and just follow them step by step. Another thing you can do, which is what sort of mathematical science has led one to come to expect, is I'll just work out the formula for the answer, and then I don't have to go through all those individual steps the system itself has to go through. I just sort of fill in a parameter to the formula and I get the result. And computational irreducibility, which is closely related to Gödel's theorem, is the statement that you often can't do that. So for example, if you want to say, will the system ever do this? The answer will be you just can't tell, because it is a computationally irreducible process, and ever is a long time, an infinite time. And to know whether that could ever happen, because it's irreducible, you also have to be able to run for an infinite time. So, okay, let's see. Okay, here's a fun one that I'm not sure I'm going to be able to say that much about, but might be fun for Mikhail again. What is the history of UFO observations? So, I think people, unidentified flying objects, kind of, have we been visited by the extraterrestrials, and have they come in flying saucers and so on, has a fun history. I don't know when the first of those things happened, but I have to believe, if you think about the history of flight done by humans, right, there were balloons back, hot air balloons and so on, back, the Montgolfier brothers was late 1700s, maybe I'm getting that wrong, something like that. I think, people ascending over Paris in these very decorated balloons and so on. So people could have started talking about unidentified flying objects around that time. I suspect, I don't think I've heard of them. The thing that was, people, I think, started really talking about those kinds of things once airplanes were common. And then there's sort of been a long running story of what is an unidentified flying object? Is it a lenticular cloud that looks like a sort of flying saucer shape, and it's a weird shaped thing? And it relates very much to this question about what is artificial and what is natural, and how do you tell? And if it's something that was made by us, it was some funky military experiment, well, then we expect it to have all the details of our kind of engineering. Although, if you see your average stealth bomber or something, it doesn't look much like an ordinary plane. It's got all these very flat surfaces that try and avoid radar reflections and so on. And it looks pretty weird. And if you were to see one of those things and you didn't know at all what had been developed in the history of our engineering, maybe because it was secret, you might say that looks like an unidentified flying object that must be, alien technology. But there's this sort of repeated thing. I mean, there's the famous, stories from the 1950s, I guess, of Project Blue Book, which was a US Air Force, I guess, project to investigate claims about UFOs. And there was a very kind of a pretty sober scientist who got kind of pulled into that whole thing, and all kinds of stories about it. Area 54 in New Mexico, where it's like, that's the fodder for the science fiction movie and so on, of where the alien spaceships are kept and all those kinds of things. But this story doesn't die. I mean, it keeps on going. And, there are things from very recent times of sort of cockpit recordings from military planes about, strange objects that are moving, many times the speed of sound, and so on and so on and so on. Again, it's very much a story of what's artificial and what's natural, because if it's terrestrial technology, we know what it's going to be like, roughly. If it's something bizarre, it's like, what's the difference between a lenticular cloud or some weird new effect, some weird new atmospheric effect, and an unidentified flying object, which kind of has the sense of being a something with sort of intentional, some pilot is at the controls type thing. So I don't think I have much more useful to say about that than that, but it is interesting. Oh, am I being told Area 51? I thought it was, maybe I'm okay. Area 51, I guess, rather than Area 54. How did I get Area 54? Maybe that's some other thing. No matter. In any case, the thing that you have fun questions then about, okay, what if there were alien spacecraft in the solar system? What if there was an alien structure on the moon? What if, how can you tell? And you get into these very complicated questions about, how do you even tell that there's intelligent life on Earth? When I was writing the New Kind of Science book, I was curious about that question. And I asked some astronauts I know, what do you see on the Earth that most seems like it's a sign of intelligent life, or intelligence or something, or intentionality? And the thing they identified actually was in the Great Salt Lake in Utah. There's this, it turns out it's a railroad causeway that slices across the lake. And on one side, the algae are one color, on the other side, the algae are another color. And there's a straight line that crosses between those two. And there's been sort of a long history of, what do you put as a feature on the Earth so that the aliens can recognize it? I think Gauss, for example, suggested chopping down trees in the Siberian forest to be in the shape of the Pythagorean theorem, so that the Martians could see that somebody on the Earth had identified the Pythagorean theorem. But you can ask kind of, how would you generalize that? And there's a long story about this, which I could tell at a different time. And it's kind of interesting to see kind of in the solar system, where are there strange geometrical things? One of my sort of favorite sort of statements about this, Immanuel Kant had this statement: if you find a hexagon drawn in the sand, then you know that must have been done on purpose, because nothing would naturally have created a hexagon. Well, it turns out, if you look at the North Pole of Saturn, that there is a giant storm that is perfectly hexagonal in shape. So that's is that extraterrestrials, is an unidentified, it's a flying object, planetary object or something, or what is that? Or is it just a storm? Complicated thing. Okay, there have been a couple of questions here about results from the LHC to do with B meson decays, and I have not seen this stuff, so I'm going to have to click on this link and take a look at this. Okay. Okay. All right, well, I can explain what this is about. I don't know I can't discuss I haven't looked enough at the actual, what was discovered there, but okay. Well, let's see, I don't know, this is crossover between physics and history of physics, but okay, I'll tell you a bit of both. Okay, so this has to do with so-called, has to do with the standard model of particle physics. Okay, let's go back a little bit. So nuclear beta decay was observed when radioactivity was discovered. Who will have discovered that? Well, Marie Curie have discovered that. Certainly in the very early days of, well, radium is an alpha emitter. I think maybe polonium is a beta emitter, I'm not sure. So there are these different kinds of radiation. When nuclei self-destruct, there's alpha radiation, which is the nucleus emits little helium-4 nuclei, 2 proton, 2 neutron lumps, or beta decay, where it essentially emits electrons and neutrinos, as it turns out, and gamma decay, where it emits photons. And so in the early days of radioactivity, I don't remember exactly when, beta decay was discovered. The possibility of nuclei spontaneously self-destructing and emitting electrons. So somewhat later, I think in the 1940s, if I remember correctly, the neutron was discovered to be unstable. So nuclei contain neutrons and protons. Protons, so far as we can tell, are completely stable particles. They have lifetimes, certainly more than about 10 to the 30th years. Neutrons, on the other hand, have a lifetime of about 15 minutes. And a free neutron, not bound in a nucleus, simply decays to a proton, electron, and antineutrino. And that process is an example of beta decay. And so then the question was, what causes beta decay? What kind of effect, what kind of quantum effect, what kind of process causes beta decay? And there was sort of a phenomenological theory of beta decay developed in the 1950s. And most particularly was a thing called the V-A theory that was developed by Dick Feynman and Murray Gell-Mann, both people I knew pretty well. That was a theory of kind of what the effective interaction process going on in nuclear beta decay was. But people didn't know sort of what the cause of that decay process was. And just like in electromagnetism, it was realized from what Max Planck had done in 1900 and so on, and then what Einstein did a little bit later, this idea of photons, discrete particles of electromagnetic radiation, which could then be studied from a quantum theory point of view. That was discovered in the 1920s. And then the theory of quantum electrodynamics developed, and by the 1940s, it was fairly under control mathematically and so on, with the invention of Feynman diagrams and things like that. But the question was, could a similar thing be done for the weak nuclear force, the thing that causes nuclear beta decay? And initially it wasn't. Initially it was just like when you have photons in electromagnetism, you exchange photons, and that's why there can be a force. Electromagnetic forces can be sort of at a distance. In the case of the weak interactions, what seemed to be the case is they were just point interactions. Everything happened at a point, and the details of what happened at that point were things that were being analyzed by the V-A is a vector kind of law, which is similar to electromagnetism, and A is the axial vector law, which is different from electromagnetism. But that was kind of a theory for how this worked. Well, one of the features, so there were a number of things that happened. One of them has to do with parity violation, was discovered in mid-1950s. So that had to do with the fact that, maybe this is, let's not go in that direction. We don't need to talk about that. There were certain rules about how weak nuclear interactions could happen, how weak interactions occurred. Actually, weak interactions happened to me. My personal sort of first sort of very serious foray into quantum field theory and things like that. And I have to say, when I was, I guess, 13 years old, I spent the summer writing this long treatise on weak interactions, which you can now find on the web. I can't guarantee that everything in it is correct. It was my 13 to 14-year-old production. But anyway, the thing that I happened to study a whole bunch. But at the time, it was very much sort of these are the phenomena of the weak interaction. We don't really know what's underneath it. But what were the phenomena? So very important phenomenon was about strange particles. So strange particles, okay, so back in the 1930s, well, people had known, okay, so the electron was discovered right at the end of the 1800s. Then the proton was discovered in the early 1900s, and then neutron and so on. So people knew about proton, neutron, electron. Then Hideki Yukawa suggested that there should be these things called pions, which were the carriers of the strong nuclear force that would bind nuclei together. Then they were not the first particles to actually be discovered separately. The first particle to be discovered separately was the muon, which actually has a very similar to mass to the pion, but isn't the pion. Muon is like a heavy version of the electron, was discovered in the 1930s in cosmic rays. And then what happened is that so there started to be this whole zoo of elementary particles discovered. But a bunch of these particles, their decay processes, even the muon, for example, it decays through the weak interaction. A muon decays into an electron and 2 neutrinos. And then the pion also, or the pi plus and pi minus, decay into a muon and a neutrino. That's their most common decay mode. The kaon, another particle that was discovered, decays into typically 2 pions. And so those decay processes were examples of the weak interaction. And what was discovered was that there were certain rules about those decay processes. So, for example, I should have explained that these different kinds of particles, the pions, the kaons, the proton, are things like the lambda hyperon, the sigma hyperons, etc. These were all particles that were discovered in the it ended up being 1950s, and a whole bunch of these things were discovered. And people started realizing that you could sort of fit these together in some kind of sort of combinatorial arrangements. It's a little bit like what Dalton had done in inventing atomic theory with respect to chemistry, by just sort of noticing that there's 2 of this and 1 of that, and so there's sort of, it must be that this consists of these discrete elements. Well, so back in the day, people like Murray Gell-Mann noticed that for elementary particles and realized that you could sort of fit them together in certain ways, and came up with this idea. Also, my friend George Zweig was also involved in this in 1964, suggesting this quark theory, where you could say that all these different elementary particles were could be understood in terms of combinations of, let's say, 3 quarks for baryons like protons, and a quark and an antiquark for things like the pion, mesons like the pion. But actually, even before that, Murray Gell-Mann had suggested this idea of this thing called strangeness. And so the question is, what's the difference between something like a lambda hyperon and a proton and neutron? They kind of have about the same mass, but they're obviously different in some way. Well, what he said was, let's imagine that there's a quantum number called strangeness, which is an attribute of lambda hyperons. It's also an attribute of kaons, and that is the characterization of those things. So the feature of strangeness is, in strong interactions, like what happens inside nuclei, strangeness can't be created or destroyed. In weak interactions, strangeness can be changed. So what that meant was, there was this phenomenon, it was called associated production, which was, if you got a lambda hyperon, you also got a kaon. And the reason that happened is because the strangenesses of the lambda and the k would cancel each other out. So the strong interaction you get by just smashing protons together would produce something which had net 0 strangeness. And that was you would see in these bubble chamber pictures, you would see these 2 particles, a lambda particle and a kaon, being produced associatedly, so to speak. And so that was kind of the strong interactions don't have strangeness changing, the weak interactions do. So then there began to be all kinds of different rules that were discovered about strangeness and how it changed in weak interactions and so on. All of it was a bit okay. So one of the things that happened was, in addition to it being possible to change strangeness, the weak interactions had this feature that whenever one of them happened, it always changed charge. It didn't, the total charge would be the same, but always there will be sort of an exchange of charge between particles in some sense. It would be, there would be something where you would have a neutron, which has charge 0, would turn into a proton with charge 1, and emit an electron with charge -1. So charge was still conserved, but sort of the mainline thing that happened was neutron charge 0 turns into proton with charge 1. Okay, So that led to the question, were there neutral currents? Were there ways of having weak interactions that would not change charge? And back when I was first studying this in the early 1970s, neutral currents were like, well, we don't think so. None of them have been observed. Okay, so it was believed that the weak interactions were always charge changing. And I have to say, as I talk to you guys about this, I realize I have not thought about this in 45 years. So I'm glad those neurons seem to be still functioning. In any case, so back in the early 1970s, how do weak interactions happen? There was a thing called the intermediate vector boson hypothesis, which said that just like there are photons exchanged to make electromagnetic forces, so there are intermediate vector bosons exchanged to make weak forces. But the intermediate vector boson would actually be a very high mass object, not something like a photon, which is zero mass, or even a pion, which is a tenth the mass of a proton, be a very high mass object. And the fact that it was high mass would account for the fact that weak interactions seem to happen almost at a point. They seem to be almost, not extended. And so that was kind of the idea there. But nobody knew if that was really correct. Then eventually along came the so-called Weinberg-Salam model, which became the standard model of particle physics, although originally it was called the Weinberg-Salam model after Steve Weinberg and Abdus Salam, both of whom Steve Weinberg is still alive, Abdus Salam is not, but I've known both of them. They kind of, in 1967-ish, proposed this kind of model of how things might get set up, how there might be a thing that is a little bit like electromagnetism, but not quite, that might be the thing responsible for weak interactions. And somehow one had to account for the fact that, well, it's just like the photon, but it has a huge mass. And the mechanism for that mass was the Higgs mechanism, and there's a whole story to that, which let me not go into that right now. But suffice it to say, eventually it became more and more likely, from kind of the mathematics working out nicely, that yes, the W particle, which was the sort of modern name for the intermediate vector boson, really should exist. It was finally observed in the 1980s, and it has a mass of about 65 times the mass of a proton, and that was all good. But this whole theory also predicted neutral currents. That is, so the W boson has a charge plus or minus 1, but also a neutral particle, often called the Z0 or the Z0, as I used to call it when I was first studying these things in British English. So prediction, there are going to be neutral currents. Okay, neutral currents had not been observed in ordinary particle decays. There were particle decays which could be produced by neutral currents, but they were not observed. And the neutral currents that would have been easiest to observe would be strangeness changing neutral currents, okay? And strangeness changing neutral currents would have led to decay processes which were not observed. For example, if I'm remembering, and this is from a very long time ago, I'm afraid, K goes to pi, neutrino, antineutrino, I think is an example of that. Yeah, K0 goes to pi 0 nu bar as an example, I think. Gosh, I wrote a whole paper about this in 1976, but I'm afraid I have forgotten some of the details now. In any case, okay, neutral currents not observed. The best way to observe a neutral current would be by a reaction that involved neutrinos. So the way neutrinos were detected originally was in these giant tanks of basically cleaning fluid, where you'd have neutrinos produced by a nuclear reactor, and the neutrinos would be streaming through this big tank. And just every so often, with very low probability, a neutrino would interact with a nucleus there, and the nucleus would kind of be kicked by the neutrino, and you would see the effect of that nucleus as a sort of piece of radiation. But that effect was mostly actually, I'm sorry. No. The correct thing, not that. That the neutrino would convert into an electron or into a muon as a result of interacting with the nucleus, and you would then observe that electron or that muon. And so that was a charge changing, because neutrino has charge 0, the electron and muon have charge 1. That was a charge changing weak interaction. So the case that is more difficult still is neutrino comes in and neutrino goes out. That's an example of a neutral current interaction. So the question was, were neutrino interactions where neutrino comes in and neutrino goes out, were they happening? And it's obviously a bit difficult to detect, because the neutrino that goes out, you don't get to see what happens with that, because it might go through the whole Earth without interacting again. It might be just it happened to interact once, and then it doesn't interact for a really long time after that. And you can potentially see it by looking at the recoil of the nucleus and things like this. So turns out, so neutral currents were discovered, I think, 1970. When was it? 1976, maybe a little earlier than that. But the embarrassing thing is, had neutral currents been looked for earlier, the experiments that had been done at CERN in the early 1960s would have observed neutral currents. They just didn't look for them. They didn't know to look for them. The theory hadn't really predicted them. And the theory had kind of said, oh, no, those don't really exist. There's no reason for them to exist. So nobody looked for them. And my late friend, Tini Veltman, always told the story that he told them to look for them, but they hadn't looked for them. And by the time he told them to look for them, actually, it was too late, because they had recycled the bubble chamber film that had been taken in the early 1960s. And had they kept it and reanalyzed it, they would have discovered neutral currents much earlier. Okay, so I believe the thing that's being talked about here is, I would have to look more at this to see, let's see, what is this? To see exactly what's being talked about. But this is, okay. Doesn't look that exciting. I see. Okay, so the claim here is that, okay, if you have a B quark, which is, so strangeness was kind of a 1950s idea, then people had suggested, just by virtue of symmetry, there are two quarks, the up quark and the down quark, that show up in the proton and neutron and those kinds of non-strange particles. Then the strange quark shows up in the strange particles, and there's sort of all possible combinations of up, down, strange make up the different particles. Just by virtue of symmetry, people had suggested maybe there's also a charm quark that is sort of the pair, just as the down quark goes with the up quark, so the charm quark would go with the strange quark. And people didn't know if that was right. Then in the mid-1970s, a bunch of things were observed, which eventually, in not very long, in 6 months or so, became clear those are evidence of charm quarks. And so, yes, the charm quark really exists. So that was like, okay, those exist. There are two generations of particles, the up-down charm, strange charm. But then there's the electron and there's the muon. And then another thing was discovered. So then in 1977, I guess, there was another unexpected discovery, which was the B quark. It has a mass about 5 times the mass of the proton. So then that was another thing. B quarks are kind of a little bit like strange quarks, a little bit like down quarks. And then much, much later, the top quark was discovered, which kind of is the partner of the B quark, and that has a mass of about 173 times the mass of a proton. In any case, there's this question for the weak interactions and the W particle and the Z particle and so on, of what what kind of weak interactions, what kind of interactions can W particles have with these different kinds of quarks. And so the most common kind of process is something like up quark goes to down quark plus W particle. That's a charge changing reaction. Or some kind of quark emits a Z0 but stays as the same kind of quark. Okay, so the thing that's not supposed to happen is that you can have a Z particle, Z0, emitted by as a result of a transition between two quarks. And so what is claimed here is that let's see, how does this work? So what's being claimed is that there's a decay of the B0, which is a combination of a B quark and, well, actually the B0S here, a B quark and a strange quark to mu1, mu plus, mu minus. I don't know, this really takes me back. This is the kind of particle physics I used to do a very long time ago. And boy, I could even work out this formula here. I even pretty much know this formula that I'm seeing in this document about the rate of the decay from of a B0 to mu plus, mu minus. And okay, so there's apparently a prediction here, and the claim would be that, let's see, is there a claim here that the results are different from what was expected? Come on. Okay, this is okay, so the claim is that the rate of the decay, B0 goes to mu plus, mu minus, is 2.5 times the prediction from the standard model. The standard model would say that decay could only happen through some fairly complicated process involving, I guess, two virtual W particles. There's an alternative process where it could happen through a direct sort of neutral current interaction between B quarks and strange quarks. I'm seeing here, oh boy, there's a kind of diagram, a kind of Feynman diagram that represents a weak process that was called a penguin diagram. And that involved two people I know, a person called John Ellis, who's was a longtime physicist at CERN, and a then young person called Melissa Franklin, who was a intern type person at CERN. And she had some kind of bar bet with John Ellis that was, if you lose this bet, you have to get the word penguin into the next paper that you write. And so John, I guess, lost this bet, and he was writing this paper about weak decay processes. And so he has this kind of Feynman diagram to represent this process, which really doesn't look anything like a penguin, but you can draw it because it's just a graph. You can lay it out however you want. You can draw it so it kind of looks like a penguin. And he did that. And these things have been called penguin diagrams ever since. But apparently that's one of the processes for this particular decay. I mean, I would say that in the world of weird effects observed in particle physics, and are they real and are they not real, it's always a complicated story because particle physics experiments are very difficult. They involve huge detectors with huge numbers of things that are detected at each event. You have to kind of parcel that out and make sure that there's no background, there's nothing that you didn't expect about, oh, there's this effect that causes this to happen when this happens and so on. It's very difficult to know. And I noticed here that it seemed like there was an effect to about 2.5 standard deviations, which is not particularly large. It's not particularly what you would expect from, not particularly extreme in terms of what you would expect from signs of statistical variations. I think this sort of question about, okay, this is the claim is it's now reached 3 sigma, all right. I would say thank you for pointing this out to me. I love these kinds of things. Back in the day, weak decays were my particular friends. I wrote a big, long review about weak decays that had a lot of very interesting things in it back in 1980, which I'm not sure anybody ever read, because at the time, weak decays were definitely out of fashion. But kind of the thing that is interesting to realize is you think it's just some random particle decaying into other particles. But the point is, what happens is, because of the way quantum field theory works, even a process which occurs at sort of the ordinary energy scales that accelerators reach, or that correspond to the masses of particles, because of virtual particle effects, it can be sensitive to things that are happening at much higher energies beyond the energies that accelerators can reach. So by looking with high precision at these weak decays, you can probe things that are beyond what we've been able to see in accelerators. And for example, the fact that the Higgs particle was known with some considerable accuracy, sort of how it would behave and so on, what mass it would have and things like that, was a consequence of this sort of ability to probe processes by looking at these virtual particle effects with high precision experiments. So they're a really worthwhile thing to do. But this is this is exactly the kind of decay process that I used to enjoy. So pi zero. In fact, I think I wrote about pi zero goes to E plus E minus, which is the analog, which is sort of analogous to what's being discussed here. And pi zero goes to E plus E minus is not a decay that can normally happen in the normal model of things because of, I think, charge conjugation parity, if I remember correctly. Is that right? The other related decay is pi zero goes to neutrino, antineutrino, which I believe has now been observed. But pi zero, the pi zero particle. Okay, now I'm just playing particle physicist here, but this is from my distant past. But the pi zero decays in about 10 to the minus 16 seconds into 2 photons. It's kind of a famous source of 2 sort of photons that, because if the pi zero is at rest for momentum conservation, the 2 photons go out back to back, so to speak. And that's anyway, the pi zero's most common form of decay is photon-photon. Those photons can each turn into, either one of them can turn into electron-positron pair. So that ends you up with a gamma and an E plus E minus, or 2 E plus E minuses. But a single E plus E minus can't happen according to, I think it violates parity or charge conjugation invariance, which means that it can't happen as a result of, so normally when you're producing photons, that's through electromagnetic processes. That's how the pi zero decays. Sort of particle physics trivia, the lifetime of the pi plus and pi minus is like 10 to the minus 8 seconds. So the lifetime of the pi zero is much shorter than that, because the electromagnetic interactions are much stronger than the weak interactions. So they lead to a shorter, they lead to sort of more rapid decay. And the question is, could you also have weak interactions contributing to some decay modes of the pi zero? And that's what I think you have to get, well, you certainly have to have it to get pi zero goes to neutrino, antineutrino, because neutrino only does weak interactions. It doesn't do electromagnetic interactions because it doesn't have a charge. Okay, long story here, but yeah, that's about as much as I could say about this. I wouldn't, just based on my history of knowing about particle physics and physics experiments in general, I would not be running around saying there's a major new kind of force in the universe based on this experiment so far. I think you have to wait a bit. These experiments are really hard, and it's both the experiment is hard in this case, and I don't know. The predictions from the standard model are probably reasonably straightforward in this case. But I since I only just learned about this, I haven't looked at them. But so I wouldn't know whether there was a possibility of a mistake, like Isaac Newton's mistake in predicting the motion of the moon based on his theory. And you shouldn't conclude his theory is right or wrong based on that, because there's kind of a stack of things that have to be calculated to work out the actual effect. All right, I better wrap up here. And I realized that there were a bunch of people asking about the history of Lisp. I promise I will get to that next time. I had hoped I would get to that this time. Very different topic. We ended up talking a bunch about physics today. and that's I hope people found that interesting. It was a lot of fun for me to think again about weak decay processes, because I last seriously thought about those things about 41 years ago. So thanks a lot. And actually, I'm about to do another live stream that's part of my day job, doing language design for the next version of Wolfram language. So, and next week in this slot, I will be doing a business and innovation Q&A, and the week after that, I expect to be doing another one of these, and I will talk about Lisp at that time. Okay, thanks.